Hi guys, welcome to 3.5 Rational Functions. What we're going to do is we're going to identify the graphs of rational functions using all the various key attributes. So some definitions. Vertical lines, remember they go up and down and they have the equation x equals some kind of number. And asymptotes are the invisible line that a function gets close to but never touches. I kind of told you that's like one of those fences that are invisible that dogs get really close to. They're like your graph. The fence is like an asymptote. It will shock the dog if they cross the fence. So they'll get close to it, but they'll never touch it because they don't want to get shocked. So the dog is like your graph. The asymptote is like the invisible boundary line. How do we find them? Well, they're the parts, the vertical lines are the ones that are separating your graph in pieces from left to right. So we look to see where our break is between the two pieces, left and right. And that invisible line is called the vertical asymptote, or VA for short. Now, a vertical asymptote, again, is that invisible line, but a hole is like an open circle on your graph, kind of like a pothole. Your graph is going along, it has a pothole, and then it keeps going. That part that's the pothole, the hole, is a discontinuity. That's where your graph is not continuous, and that's something we have to know about. So they're represented as an open circle. And again, we have to note them. So let's start with some things that we learned last year. We're going to find the domain first. How do you find the domain? Well, you start by factoring your numerator and denominator. So my fraction here, I go over to it. He doesn't need to be factored because they're both top and bottom to the first power. Then, to find that, remember back when we started talking about these things, we learned that fractions, you can't have 0 on the bottom. So what we're going to do is we're going to find the bad spots by setting the bottom equal to 0. Only the bottom. So x is 3. That's the bad spot in the domain. That's the break in the domain. So the domain is all real numbers except for 3. That's it. We just found the domain. It's everything except for 3. That's probably where there's a vertical asymptote or a hole. Now this question asks us to find the vertical asymptote. So we start by factoring top and bottom and canceling if needed. No canceling, no factoring needed. Set the bottom equal to 0 and solve for x. So in this case, we're finding the vertical asymptote. The vertical asymptote is the break in the domain. It's at the line that's invisible at x equals 3. That was pretty easy. Now, this question asks us to find the holes. And that's the open circles. So we're going to start it just the same. We're going to factor top and bottom. Oh, these actually do factor. Look, that's quadratic trinomial. So I'm going to do my big X. A times C is 2. B is on the bottom. What numbers multiply to give me 2 but add to give me 3? That's 2 and 1. Divide by A. So the top of this becomes, x plus 2, x plus 1, because I actually can factor the top. Oh, and I look at the bottom, I can factor him too. I'm going to do his big X. A times C goes on top, B goes on bottom. Who multiplies to give me negative 3, but adds to give me negative 2 is negative 3 and 1. Divide by A, which is 1. And look at that, I get x minus 3 and x plus 1. So I just factored the top and bottom. I'm going to see if there's any common things to cancel. Any like factors. Well, x plus 2, he didn't match anyone. Ooh, these x plus 1s match. X minus 3 doesn't match anyone. It's the guy that we are canceling that we set equal to 0. So x plus 1 equals 0, because we canceled him. He's the whole. He's the whole. The thing that I canceled is at -1. There's an open circle in my graph at -1. Open circle in my graph. Awesome. All right, now we're going to get some more definitions. Lines that go side to side are what we call horizontal asymptotes, or horizontal lines. And and an asymptote is the ones that are invisible on our graph, that our graph is going to get really close to but doesn't cross. And they have the form y equals a number. So on this graph, HAs are the ones that separate your graph from top to bottom in pieces. VAs separate them left and right. HA separate them top and bottom. Remember, they're the invisible lines. So, to find them, there are 3 cases, and I have 3 examples here. And you have to look at the degree. Remember, that's the highest exponent in the top, and the degree in the highest exponent in the bottom, and compare them. You either have the top is smaller than the bottom, bigger than the bottom, or equal to the bottom. So let's look at those. There is no x up here, so his degree is 0. This one down here is 1. 0 is less than 1. This one, the exponent is 2, so the degree is 2. Down here it's 1, so 2 is greater than 1. Here the highest exponent is 1 on top and bottom, so that's the equals case. Now, if it's the less than case, right here, less than, then we automatically know that the answer is the HA is at y equals 0. If it's the greater than case, we know that there's automatically no HA. It's probably a slant asymptote, if anything. And if it's unfortunately, the equals case, then the HA is the ratio of the leading coefficients. That means in this case, it'd be 2 over 1, because you go to the big numbers, leading coefficients, in front. So y equals 2 would be your HA in this case. Let's go see some examples. All right, this one says find the HA. So what I'm going to do is I'm going to check the highest and lowest exponents. So that degree is 2. That degree is 2. That's the equals case. So according to it, I go to the big coefficients in front. So y equals 4 over 2. So that means 4 over 2 is 2. My HA is at y equals 2. That means there's going to be an invisible line separating the top from the bottom at y equals 2. All right, let's try this one. So I go and I look at the top. He's got a 1 for his highest exponent. Down here it's 2. That's the smaller case. That means that the HA is automatically at 0. So that means the top and bottom is separated by an invisible line at y equals 0. Okay, let's try this guy. His exponent's 2. His exponent degree is 1. That's the greater than case. So on an HA, there is none because it's the greater than case. That means there might be a slant asymptote if there's anything at all, but there's definitely no horizontal line separating the top and the bottom. Now about those slant asymptotes. If the degree of the numerator is exactly 1 more than the degree of the denominator, then you have a slant asymptote. So an example of that would be this guy here has the highest exponent's 2. The highest exponent here is 1. 2 is 1 plus 1. 1 more than the bottom equals the top. So this one has a slant asymptote. Now, how do we find them? We're going to do synthetic division and keep the quotient. So let's see if this one even has one to begin with. Squared first. 2 is 1 bigger than 1. So he has a slant asymptote, and the way we find him is synthetic division. Well, you could use polynomial long division, but I'm not all for that because it takes too long. So I have 3x squared plus 4x minus 5. You still need to make sure that they're in order from highest to lowest exponent and that nobody's missing. You put a 0 in for them. That one was good. Now over here, x plus 3 becomes negative 3. Remember, you change the sign when it's with an x. Now let's do some long division. Bring down the first number. And remember, it's multiply, add until you get to the end. So multiply by the outside. 3 times negative 3 is negative 9. And then add the column. 4 and negative 9 make negative 5. Multiply again. Negative 5 times negative 3 is 15. Add the column. Negative 5 plus 15 is 10. And now we analyze it. Remember, this is the remainder, the constant, the x. Remember, it keeps getting bigger. So my answer, which is also the slant asymptote, is just the quotient. Y equals 3x minus 5. The remainder you do not put. And it's only when the degree of the top is 1 more than the degree of the bottom. You'd find the quotient and keep it. Now, intercepts. X-intercepts, you set the numerator equal to 0. Y-intercepts, you substitute 0 in for all the x's. So let's find some intercepts. Well, you should factor it first because that's going to get rid of some things that you don't need. So I'm going to factor using the big X. Oops, let me go back. There we go. Here's my big X. And on top here, A times C, B on the bottom, multiplies to give me 2 times 1 is 2, adds to give me 3, divide by A. So this one on top, I have x plus 2, x plus 1. On the bottom, he's a squared also, so I'm going to factor him using the big X. A times C is negative 3, negative 2 for the B. What multiplies to give me that is negative 3 and 1, divide by A. So I get x minus 3, x plus 1. And I did this because some stuff cancels. The x plus 1s are like factors. So now I'm left with x plus 2 over x minus 3. And according to this, it wants me to find the find the intercepts. To find the x-intercept, you set the top numerator equal to 0. So I have an x-intercept at negative 2. To find the y-intercept, you plug in 0 for all the y's. So the y-intercept is at negative 2/3. Those are my two answers for the x and y-intercept. All right, now this one tells us to put it all together for the domain, the holes, the asymptotes, the intercepts. Woohoo, here we go. So the first thing I'm going to do is make sure everybody is factored. So up on top, this is the first power, but these can take out a GCF of 3. 3x divided by 3 is x. Negative 6 divided by 3 is negative 2. On the bottom, that's a squared, so I can use the big X. So A times C is negative 8. B is 2. What multiplies to give me that? Be 4 and negative 2. Divide by A. So I get x plus 4, x minus 2. Now I'm going to kind of take these out of order a little bit first thing I'm going to find is domain. So my answer for domain is, I'm going to set the bottom equal to 0. So I get basically -4 and +2. So all real numbers except -4 and +2 is my domain. Now, for wholes, remember wholes are things that we canceled. So if I take x minus 2 and cancel those, x minus 2, when I set it equal to 0, I get 2. So there's a hole at x equals 2. And then I might as well find that vertical asymptote while I'm at it. The VA, after you've canceled, you now have 3 over x plus 4 left. So your VA, you set equal to 0, the denominator. Well, we've already done that. That's -4. So my vertical asymptote is at x equals -4. That's the little up and down invisible line. And I need to also go and look at this guy and see what my HA could be. Now, HA, we find that by going and looking at the degree of the top, degree of the bottom. 0 is smaller than 1. So that means my HA is at 0. That means the top and bottom are separated by a dashed or invisible line at 0. Now, intercepts. The x-intercept you get by setting the top equal to 0. Well, 3 equals 0 makes no sense at all because 3 never equals 0, so there is no x-intercept. And I'm going to have to put him over here a little bit. X-intercept, none. Now I'm going to go do the y-intercept. The y-intercept, you take your function, and you plug 0 in for all the x's. So I get 3/4. So my y-intercept is at 3/4. So I'm going to put him right here. The y-intercept is at 0,3/4. There's my answers. I put them all here at the top so it'll be easier for you to find them. And you know what I'm going to have you do next. You're going to put all this stuff on a graph, right? All right, that means we have to find all that stuff. Well, it's a good thing we just did this problem. So up here on the top, you can GCF factor out a 3. Down here on the bottom, you can use the big X to get that this was x plus 4, x minus 2. We saw that the domain on this was all real numbers except at -4 and +2. Now, the domain that was useful to know is all real numbers except for -4 and +2, because remember we set the bottom equal to 0. And then we canceled. We said x minus 2 is where our whole, so x equals 2, because you set that equal to 0. That's where the whole is. So I'm going to have an open circle on my graph at 2. Then all I had left over here was 3 over x plus 4. When you set that bottom equal to 0, that means that the VA is at -4. So the VA is at -4. Then we move on a little further. We look at the top's degree, the bottom's degree. That's the less than case. So the horizontal asymptote was, y equals 0. Then we got to do x-intercepts. So x-intercept was you set the top equal to 0. Remember we said there was none. So there is no x-intercept. And then the y-intercept, remember we set 0 in for all the x's. So the y-intercept was at 0 3/4. Now, we're going to put all this on a graph. So we've already written all this stuff down. And I'm going to kind of erase that. Actually, you know what? I don't have to erase all that. We're just going to put a big axis right here and hope we can fit him in. Okay. Here's the x and the y-axis. And what do we know? We know at -4, we have a vertical asymptote. So I'm going to put him on first, because he's going to be the easy one to draw. There's my VA. So I got him. Now we also know there's an HA at 0. So hi HA, we're going to put you on there. There's our fences. Now I'm going to start putting x-intercepts. So an x-intercept, there is none. Then over here at 3/4, so on the y-axis, up almost, but just at 3/4 high, is my y-intercept. And then at 2, I have a hole. So I'm going to have to be careful as I'm drawing this. So what am I drawing? Well, I'm also going to make sure I put my x over here at 2. There's going to be a hole somewhere. Now we know that our dogs, that's the points, are going to run towards the fences, but never touch them. He's going to go this way too, but remember he has a pothole up here at 2, and he's going to keep getting closer to this fence, but never touch it. And then one thing we learned last year is about their symmetry. They have origin symmetry. So what's going on in one diagonal quadrant will be a reflection down here. So these are reflections of each other. And again, our dogs or our graph is going to get close to the fences but never cross them. So there we are. We've sketched him. And there's a better picture. There's our hole, our y-intercept, our VAs and HAs, and our graphs going towards our asymptotes. All right, let's try another one. So for this one here, let's see about factoring him. Up on top, I've got cubed, but these are both x's, so I know I can take an x out. When I do that, that gives me x squared minus 9, because that's the GCF, is x. So cubed divided by x is squared, negative 9x divided by x is negative 9x. And I also know that that can be factored. That is a difference of 2 squareds. So x plus 3, x minus 3 is the same thing as x squared minus 9. Now I'm going to look at the bottom. That one I'm going to do the big X on. So 1 times 12 is 12. Put negative 7 on the bottom. So that's negative 3 and negative 4 divided by A. So x minus 3, x minus 4. And before I get started on him, I know that the domain, we set the bottom equal to 0. And that'll give us 3 and 4. So all real numbers except 3 and 4. Then I go ahead and cancel. X minus 3. So when you set that equal to 0, you get 3. So that means I have a hole at 3. And then I make sure I rewrite this fraction. That's x plus 3 on top. And on bottom, it's x minus 4. So to find the VA, you set the bottom equal to 0. Well, that's 4. So there's a VA. Whoa. Sorry about that. Let me go back to where I was working this. Aw, man. He's all gone. So our domain, we had r not equal to 4 and 3. Let me go ahead and rewrite this guy so you can see him. Remember, we took out an x plus 3, x minus 3, over x minus 3, x minus 4. And we had found that our whole was at x minus 3. So that means he's at 3. I can't write today. I'm trying not to make it do that again on you. We also found that when we reduced this, it gave us x plus 3 over x minus 4, that our VA is at 4. There we go. And now we're going to do our horizontal asymptote. Well, our highest exponent is squared. And down here it's 1, so 2 is bigger than 1. Uh-oh. And it's 1 bigger, so that means we actually have a slant asymptote. So our HA is none. Let's go find that slant asymptote. And we also have to find the x and y intercepts. So I'm going to go ahead and distribute that. X times x is x squared over 3x. And then x minus 4. Because I want to do and find that slant asymptote. So 1x squared plus 3x plus no numbers. Remember, you have to put in a placeholder of 0. Negative 4 becomes 4. Bring down the first one. Multiply. Add. Multiply. 7 times 4 is 28. 28 and 0 make 28. So we have a slant asymptote. Remember, this is remainder, number, x. So our slant asymptote is at y equals x plus 7. So I'm going to put him up here. Y equals x. So slant asymptote is at, oops, let's make him blue since we were doing HAs that color. So slant asymptote is at y equals x plus 7. Now we have to find our x and y intercepts. So our x-intercept means that we take our top, and I'm going to go back to that fraction because he's already factored, equal to 0. So it gives us 0 and negative 3. So we have two x-intercepts. We have one at 0 and one at negative 3. And last but not least, we're going to do our y-intercept. And that's where we plug in 0 for all the x's. And I'm actually going to go to that one because it's easier for plugging in zeros. 0 squared plus 3 times 0 over 0 minus 4. So you get 0 over negative 4, which is 0. So you have a y-intercept right there at the origin at 0. Now we're going to put it all on a graph. So I'm going to draw our big, huge graph. And let's see what we've got. Let's start with our just numbering. Let's see, 1, 2, 3, 4, 5, 6, 7. Why did I go up to 7? Because I know that slant asymptote has a y-intercept of 7 and a slope of 1. So I'm going to go one more. So up 1, over 1. And that is the slant asymptote. See how he's slanted? That's where he gets his name. Wow, he's pretty. All right, now I have a VA over at 4. So 2, 3, 4. And that's the VA. areas. I have x-intercepts at 0 and -3, so 0 and -3. I have a y-intercept at 0 also. I have no HAs. I have a hole at x equals 3. So I'm going to keep that in mind. There's going to be a hole coming off of x equals 3 when I start drawing my graph. All right. Anybody else that I have? All right. Well, this guy is going to be drawn so that he can go towards our fences. So I'm going to start drawing our little graph. Well, he's got to go through these intercepts here somehow and our hole, and he's got to be close. So he's probably coming down like this to go along. And our hole, where's our hole at? At 3. And so he's probably somewhere around here going down towards it as well. And then diagonal of that would make up here. And I'm just checking to make sure all my numbers are right because something feels weird about this. So 3 and 4. So 4, got him. 3 for the hole, got him. After that is x squared x plus 3x. The bottom was x minus 4. 1, 3, 0. Divide 4 in there. 1 times 4 is 4. That's 7. 7 times 4 is 28. Okay, that's good. That looks great. X-intercept. That's the top. Equal to 0, so 0 and -3. The y-intercept. Okay, I guess he does look good. I've sketched him in there. And that was the whole culmination. That's what y'all are trying to do. There's a picture of him. I guess mine wasn't too bad. See, there's the hole down there. Here's your 2 x-intercepts where it's kind of our fence, our guys going towards the fence here on both sides. Over here, they're going in diagonal. They're going towards the fence also.